So today we're going to be looking at the speed of sound. Now, we've talked about waves with the last experiment. Today we're going to go a little bit more in depth. Specifically, we're going to look at a different type of wave for this experiment. But like we know that we can get a oscillating wave right here, and that the antinodes represent the maximum height of the wavelength, and that the nodes will be the 0 point, or the point where there's no vibration. But yeah, the wavelength is just the length of one full cycle. So wavelength is denoted by lambda, and you'll see that lambda will spread from starting at here, ending at here. So it'll make one full cycle. And this one complete cycle is called a period. So then we'll move on to the frequency, which is just the number of cycles per time. And then the amplitude is just the, like I said, maximum displacement. And like we learned last lab, there was a relationship with velocity and frequency, which is given here, where frequency is the inverse seconds, also known as hertz, denoted as Hz. And lambda is just going to be the unit of length, centimeters, meters, that type of length. And so, like I said, there's two different types of waves. Last experiment, it was specifically transverse waves. This time, we're going to be looking at longitudinal waves, where these waves, they travel along a medium, where the medium is pushing the stuff through, the wave through. And so with medians, so if you don't know what a median is, medians are things like sound, water, anything that sound can travel through. There's no medium in space, so sound cannot travel in space. So yeah, mediums, different types of mediums change the speed of the sound, and here is just a small equation where the speed of sound is equal to 331.4 plus 0.60 times temperature, and this temperature is in Celsius. And so when we're looking at the actual experiment, we're going to have a big long tube that has water slowly rising, filling up the tube. The tube just has an air column, and then the water will rise up, shortening the air column. And when you hit the tuning fork, it produces a frequency. If you hover the tuning fork over the tube, it then starts to make a wave inside, and as you adjust the water, you'll also adjust the wave. And so the wave will then create a very, very high-pitched sound. This high-pitched sound, when you hear this high-pitched sound, you'll know that you're at the antinode of the wave. The antinode should be located at the very top of the water tube thing. So right there at the very top is where you'll hear the sound, and it's going to be much, 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 much louder than the actual tuning fork. And yeah, that's it. That's the experiment. So we're just looking at longitudinal waves, which sound will be traveling through air, and we will talk about the effects it has as it travels through different mediums. And yeah, that's it. That's everything. This is going to be the procedure portion for the speed of sound. It's really simple. It's just maybe the difficult part is finding the exact point where you can hear this loud tone. First things first, we need to get the temperature of the room that we're at. That's going to be provided for you in the data table. The next thing that we need to do is, well, we're going to be using two different frequencies. We have one at 288 frequency and another one at 320. And I will demonstrate it with the 288 frequency. Record this value and raise the water, raise the cup above the water, and we're going to tap the fork, the tuning fork, and we're just going to hover it over the tube till we hear that loud pitch. So just like this. We'll adjust. So we adjust the bucket to lower the water. We just lower, to lower the water, we raise the bucket. To lower the water, we just lower the bucket. And the second one should be down here. So the first tone that you hear, the first high-pitched tone, will be L1. The second high-pitched tone will be L2. So L1 will be closer to the top, L2 will be closer to the bottom. But you're just trying to find that maximum amount of tone, where it sounds the loudest. You'll do it a couple times with the same frequency. Do it 3 times. You'll calculate the velocity of sound. You're gonna get the average of the velocity of sound, and you're going to get the percent error with that average versus the equation from equation 1, and use your average to calculate the percent error of the frequency.